In chemistry, the molar mass m is a physical property defined as the mass of a given substance divided by its amount of substance. The base SI unit for molar mass is kilogram per mole. However, for historical reasons, molar masses are almost always expressed in gram per mole. As an example, the molar mass of water, M69981800000000000000018 grams per mole. Molar masses of elements. The molar mass of atoms of an element is given by the atomic mass of the element multiplied by the molar mass constant. Mu equals 1 times 10⁻³ kilograms per mole equals 1 gram per mole. M equals 1.00797 times 1 gram per mole equals 1.00797 grams per mole. M equals 32.065 times 1 gram per mole equals 32.065 grams per mole. M equals 35.453 times 1 gram per mole equals 35.453 grams per mole. M equals 55.845 times 1 gram per mole equals 55.845 grams per mole. Multiplying by the molar mass constant ensures that the calculation is dimensionally correct. Atomic weights are dimensionless quantities, whereas molar masses have units. Some elements are usually encountered as molecules, e.g., hydrogen, sulfur, chlorine. The molar mass of molecules of these elements is the molar mass of the atoms multiplied by the number of atoms in each molecule. M equals 2 times 1.00797 times 1 gram per mole equals 2.01588 grams per mole. M equals 8 times 32.065 times 1 gram per mole equals 256.52 grams per mole. M equals 2 times 35.453 times 1 gram per mole equals 70.906 grams per mole. Molar masses of compounds. The molar mass of a compound is given by the sum of the standard atomic weight of the atoms which form the compound multiplied by the molar mass constant. Mu. M equals 22.989769.28 plus 35.453 times 1 gram per mole equals 58.443 grams per mole. M equals plus 22 times 1.00794 plus 11 times 15.9994 times 1 gram per mole equals 342.297 grams per mole. An average molar mass may be defined for mixtures of compounds. This is particularly important in polymer science, where different polymer molecules may contain different numbers of monomer units. Average molar mass of mixtures. The average molar mass of mixtures can be calculated from the mole fractions of the components and the molar masses. It can also be calculated from the mass fractions of the components. As an example, the average molar mass of dry air is 28.97 grams per mole. Related quantities. Molar mass is closely related to the relative molar mass of a compound, to the older term formula weight, and to the standard atomic masses of its constituent elements. However, it should be distinguished from the molecular mass, which is the mass of one molecule and is not directly related to the atomic mass. The mass of one atom, the Dalton, symbol Da, is also sometimes used as a unit of molar mass, especially in biochemistry, with the definition 1 Dalton equals 1 gram per mole. Despite the fact that it is strictly a unit of mass times 10⁻27 kilograms, molecular weight and formula weight are older terms for what is now more correctly called the relative molar mass. This is a dimensionless quantity equal to the molar mass divided by the molar mass constant. Molecular mass. The molecular mass is the mass of a given molecule. It is measured in atomic mass units or daltons. Different molecules of the same compound may have different molecular masses because they contain different isotopes of an element. The molar mass is a measure of the average molecular mass of all the molecules in a sample, and is usually the more appropriate measure when dealing with macroscopic quantities of a substance. Molecular masses are calculated from the relative atomic masses of each nuclide, while molar masses are calculated from the atomic mass of each element. The atomic mass takes into account the isotopic distribution of the element in a given sample. For example, water has a molar mass of 18.0153 grams per mole, but individual water molecules have molecular masses which range between 18.010564-6863 U and 22.0277 U. The distinction between molar mass and molecular mass is important because relative molecular masses can be measured directly by mass spectrometry, often to a precision of a few parts per million. This is accurate enough to directly determine the chemical formula of a molecule. DNA synthesis usage. The term formula weight has a specific meaning when used in the context of DNA synthesis. Whereas an individual phosphoramidite nucleobase to be added to a DNA polymer has protecting groups and has its molecular weight quoted including these groups. The amount of molecular weight that is ultimately added by this nucleobase to a DNA polymer is referred to as the nucleobase's formula weight. Precision and uncertainties. The precision to which a molar mass is known depends on the precision of the atomic masses from which it was calculated. Most atomic masses are known to a precision of at least 1 part in 10,000, often much better. This is adequate for almost all normal uses in chemistry. It is more precise than most chemical analyses, and exceeds the purity of most laboratory reagents. The precision of atomic masses, and hence of molar masses, is limited by the knowledge of the isotopic distribution of the element. If a more accurate value of the molar mass is required, it is necessary to determine the isotopic distribution of the sample in question, which may be different from the standard distribution used to calculate the standard atomic mass. The isotopic distributions of the different elements in a sample are not necessarily independent of one another. For example, a sample which has been distilled will be enriched in the lighter isotopes of all the elements present. This complicates the calculation of the standard uncertainty in the molar mass. A useful convention for normal laboratory work is to quote molar masses to 2 decimal places for all calculations. This is more accurate than is usually required, but avoids rounding errors during calculations. When the molar mass is greater than 1000 grams per mole, it is rarely appropriate to use more than 1 decimal place. These conventions are followed in most tabulated values of molar masses. Measurement. Molar masses are almost never measured directly. They may be calculated from standard atomic masses, and are often listed in chemical catalogs and on safety data sheets. Molar masses typically vary between 1 to 238 grams per mole for atoms of naturally occurring elements, 10 to 1000 grams per mole for simple chemical compounds, 1000 to 5 million grams per mole for polymers, proteins, DNA fragments, etc. While molar masses are almost always, in practice, calculated from atomic weights, they can also be measured in certain cases. Such measurements are much less precise than modern mass spectrometric measurements of atomic weight and molecular masses, and are of mostly historical interest. All of the procedures rely on colligative properties, and any dissociation of the compound must be taken into account. Vapor density. The measurement of molar mass by vapor density relies on the principle, first enunciated by Amedeo Avogadro, that equal volumes of gases under identical conditions contain equal numbers of particles. This principle is included in the ideal gas equation, where n is the amount of substance. The vapor density is given by combining these two equations gives an expression for the molar mass in terms of the vapor density for conditions of known pressure and temperature. Freezing point depression. The freezing point of a solution is lower than that of the pure solvent, and the freezing point depression is directly proportional to the amount concentration for dilute solutions. When the composition is expressed as a molality, the proportionality constant is known as the cryoscopic constant and is characteristic for each solvent. If W represents the mass fraction of the solute in solution, and assuming no dissociation of the solute, the molar mass is given by boiling point elevation. The boiling point of a solution of an involatile solute is higher than that of the pure solvent, and the boiling point elevation is directly proportional to the amount concentration for dilute solutions. When the composition is expressed as a molality, the proportionality constant is known as the Abelius-Koppik constant and is characteristic for each solvent.